about SIMD vectorization. And my name is Kent Melfeld, and you can pick up these slides at the tiny URL mentioned or shown down here at the bottom of the page, tinyurl.com/tac-openmp-2017. And if you look for the SIMD slides, SIMD in the title, you can pick up these and have them for later or use them on your laptop to watch what's happening without looking up at the screen. Okay, so the learning objective today is to go over what vectorization or SIMD is and look a little bit at, where it was in the past, the present, and possibly a little bit of future, and look at the idea of data dependencies and what that means for vectorization. Then we'll discuss actually what does happen in vectorization, talk about code transforms, and then we'll look at the SIMD directives that OpenMP has recently come up with for having the loops vectorized or SIMDized, and then actually having functions that can be used, how to create functions that can be used within loops that actually get vectorized within the loop, basically inlined as vectorizable units of work. And then we'll look at SIMD and threading, combining, say, work sharing and the SIMD constructs in OpenMP, and then look at some things beyond those directives to have you be able to obtain a little bit more capability from the resources. So first of all, what is SIMD? It stands for single instruction, multiple data, and it applies basically to having a single operation working on multiple data elements. And we'll see a diagram of what that means. It's good pictorial, so you get a good feeling about what it is. It's also known as vectorization. That's how it started off many years ago. At Cray in the 90s, they had vector units that had 64 double precision wide capability, whereas today we're not even there yet, but getting there. And what Cray did was bring parallel processing at the instruction level, and then what happened in the 90s, the killer micros came along, and they had processor speeds that were so fast that they just had a unit working on single instructions, not multiple data. And then around 2003, microprocessors went through a transition where they thought, oh, this is a good idea to have vectorization or SIMD instructions to get more performance out of these processing units. And so we live in a parallel universe because we are computing at parallel at many different levels. At the node levels, we have big machines that have 6,000, 10,000, 50,000 nodes. We have lots of cores within those nodes. That's another level, and you use that in terms of work sharing for the threads. That's a level of parallelization. And then at a level closer down to the guts of the hardware, we have vectorization or SIMD units that work on different data elements at the same time in parallel. So we have, there's lots and lots of levels of parallelism in computing that we use to make codes run fast and get a lot of results. And then so understanding the OpenMP SIMD directives is a good place to start for getting performance out of your code. You could go down to a level at the instruction set. And so the instruction set that they had for the vector machines was very simple and somewhat limited in what it could do. The the instruction set for working with these parallel units is a lot more complex, and you can even do things at the instruction set level to optimize things. And assembly level, and they have special instructions for getting close to that, but most people don't want to spend their life optimizing their code. They want to do their science and optimize their code, but not spend their life, as I said, doing the optimizing their code. They want to be able to do it at a high level and try things and then move on. So in the old world, or what we call the scalar world, we have some register files or registers where usually in a register, it would only hold a double precision number in that register. That was all. And so you pulled things out of the register. You did an operation here. So this was the load part. This was the operation and the store here. So we'd have the data coming in, streaming in from the registers, a single operation, say on 2 elements at a time, and then a result, and then going back to the register and eventually out the memory. And so in the new world, when we have these vector units that can do the same operation basically on multiple data. So here, instead of streaming in 1 element, I have these big registers that can hold, say, 4 or 5 double precision words in that single register. And I have that single register come over here as sequential elements that I need to be multiplied, say A elements, multiplied into B elements. And each one of those operations can occur independently. They're not dependent upon each other. And so we get a load of the whole register over here into this vector unit, and then it will then take A0, B0, multiply them together at the same time as A1, B1, C0, and C1, or ABs, A over here and B over here. It would take each element singly and multiply those together, and then put the results in a result registers over here, and then put them back over to the register file or the other registers here. So we have operations that occur simultaneously and independently there. And that's, of course, sort of the same thing you were doing with creating work sharing loops, is that you would have a thread taking the loop, and you'd have independent iterations for the loop, independent work in there for each iteration. And so you could spread those across different threads. Well, it's the same way with vectorization. You have independent operations for different data, like the different loop iterations, and you can have that done simultaneously. And so think about that. If you now have the capability to do multiplies at one result every clock period, no, that's okay. You're doing that at a gigahertz, at some gigahertz. And now if you can do 8 of them simultaneously in most of your calculation, or say it's a matrix multiply, then if this is coded right, you should be able to have it run 8 times faster than over on the scalar unit than actually doing it in scalar mode. So there's a big advantage here to vectorizing loops in your code at this level. Now, if you could, of course, do things at the thread level, and if you're only working on things in scalar mode here, fine. You've actually used more cores in your calculation. That's the upper level parallelism. But if you make sure that your loop is vectorized and can do 8 operations in a single clock period compared to the one over here, then you're going to get your results faster, and you're going to be using the machine much more efficiently. Okay, So what these registers look like, or the sort of evolution of things, is that Intel started some time back, and they had these 108-bit wide registers, and 64 bits is 8 bytes, and that holds a double precision word. So a long time ago, with the 64 bits, that would hold 2 double precision words, and this allowed these 2 data points to come into the vector unit at one time and be operated on by another set. And so your vector lengths were 2. Yes, Jason. Okay. Excellent. Okay. So for the case of 64-bit wide registers, we can have 2 double precision words in there, or 4 single precision words in there, and that's the length and the opportunity that if the loop is vectorized, it runs twice as fast if you're using double precision, or 4 times as fast if you're using single precision in your calculation. And so the evolution in terms of the instruction set on the systems was SSE, or AVX112. In this case, in the SSE AVX256, the registers are 256-bit. And then for AVX 512, which will hold up to 8 double precision numbers. And as I said, down here 4, and then just 2 sometime back. So the machines have evolved quite a bit in terms of vectorization capability in the few years, I guess, well, it's actually 13 or 14 years since early 2000 time frame. So as with making a work sharing a loop, what you can do, or what the compiler does, is tries to determine if the loop iterations are independent, and that there are independent operations. That is, you could take any iteration in this loop and put it in any particular order. That's as a true sign that the iterations are independent, is that they could be done in any order. Therefore, they could be done by any thread, or the iterations in here could be done in parallel in a SIMD unit. So to exploit it at the loop level, SIMD operations, the compiler will vectorize these types of loops and execute them as simultaneous operations in the SIMD units. And so it's not only about just having the capability of executing operations simultaneously. It's important about having the things in cache to do the operations. It's important to also have the words on, are actually the arrays on aligned, so that when they are fetching them and putting them into from memory into these registers, that it can do it in an efficient way. And another thing is sometimes it's necessary to instead of to prefetch variables when it's understood it might be in memory and take a long time to get, while other things are in a register. Then having prefetching things from memory can save in terms of eliminating latency to fetch things from memory, and they call that prefetching. And then, so the data arrangement's also important. in working with vector units, you want it coming into the registers with stride 1. That's the best way to access things, as opposed to having a stride. When things are delivered from memory into the caches, they come in units of a cache line, which is going to be 8 bytes. And if you're striding by 8 words in your loop to access things that are in some array, then you're bringing a whole cache line, 8 bytes, into the register, because that's the units it works with, and it comes into the registers that way. And if you're only using 1 because you're striding by 8, then you wasted a lot of bandwidth just to get 1 element. It's better to have those to stride through your loops and through those arrays sequentially as stride 1. And so that's another reason why you'll hear people talk about an array of structures that you see people might use, and then you're accessing things out of those different structures. Well, usually they're not going to be close in memory, and so you'll bring at minimally, well, or usually a whole cache line of information in and just use 1 element when you have an array of structure. But if you have a structure of arrays in that structure, have that type of data layout, you usually in your loops, then when you're accessing these elements out of the array, they're sequential, and you're usually accessing them at stride 1. So one of the nice things about the vector instruction set for modern processors, or the ones recently, is that you can have even if statements in your do loops, and those will vectorize. It does that by masking things with a mask bits to say whether I accept the results or not. And so many years back, if you had a single if statement in a do loop, that absolutely would not vectorize. And now with these masks, they can vectorize do loops with if statements. Not all of them, but some of them they can do, which is get you much better performance, of course. And as I said, the compiler will try to vectorize things, but it takes a conservative approach in that it wants to make sure everything is correct and not step out of its bounds in terms of assuming anything. Okay, it does some checks, but then you could spend a lot of time having the compiler double check things and do much more analysis, but it'd take all day to get your compilation back. And so it does the best effort approach, but it can be very conservative at times. And the whole idea here is, if you know that a loop can be vectorized, that the iterations are independent, you can specify that you know better and you want to override its rules for vectorization. And that's basically what the SIMD pragma originally came out for. It was just SIMD. It said, this loop is a SIMD, and I don't care what you're thinking. I know it's all the operations in there per loop are independent, and that it can be done in parallel, so do it. And then there were a lot of tag-on things after that, and in terms of ensuring better performance with the alignment and things like that. And so you have all these, you have SIMD pragmas with a lot of different clauses to specify that you understand some property about this that the compiler may not understand, and you're going to guarantee it. And that's the thing about using the SIMD pragma here, is that you're guaranteeing it to be a certain way and telling the compiler to vectorize it. And you better be right, because if you're not, then of course you're going to get screwy results. And so it helps or force, but I like to say it forces a compiler to use the SIMD instructions. And different vendors have, well, with the compiler folks, have different directives for their compiler to use. But what happened with OpenMP is they said, we're going to make this a standard. So with a compiler that is OpenMP compliant, we'll have these SIMD operations that you can use. And of course, whenever you're coding, it's a good thing to use the optimized libraries whenever possible. Don't try and reinvent the wheel to do a matrix multiply or a vector times a matrix. These libraries have been extremely optimized and vectorized to do this for you. And usually it can do much better than you. And so what happens for the compiler, when it sees a loop with independent work in there, it will, you can think of as unrolling the loop. So here, this in terms of executing this loop on a processor without any vector units, it will just sequentially go through the loop, increment I, do this operation, come back to the top of the loop, increment I again, do this operation like that. And the best way to think about what's happening for the compiler when it sees that this is independent work, think of it as being unrolled. And if you have 4 wide vectors, it'll maybe unroll it 4 or 8 way out here. And then basically it says, stream these values into my register and these values into my register, and now pull this set and then form the product and put them into A over here. And so one way to easily figure out if your loop is vectorizable is just say unroll it yourself and take all these elements here and say I'm going to put all the values in here and do the operations, and now put it over here on the other side. I'm going to do all my reads first and then all my writes. And if that gives you the same result as if you went in through it serially, yeah, then it's vectorizable. So that's an easy way to say, I know that this is a vectorizable loop like that. And of course, this is a very simple loop, and loops can get very complicated, and the compiler does a lot of dependence studies, but then analysis, but it also, that's right, I need to do this over here, but when it has more than one statement and values in here, then it will unroll that so many times. Think of it as doing this way, and then it puts these all together and thinks, oh, each one of these statements in here can be done independently. And so what I'm going to do is write those as a group of sequential accesses here, and then I'm going to stream the C's and B's into memory or into my local registers, and then these are going to go into the vector units as a group of 4 or 8, and then be multiplied and stored in the A structure over here. So that's all there is to vectorization. But of course, vectorization it gets a lot more complex for complex loops. And so sometimes you need to help or force the compiler to do the independent operations, because you know they're going to be independent, and if it's vectorized, of course, you can make your code run faster. How do you know what it's vectorized? Intel does a nice job of providing options to specify reporting and get a lot of details, the kind of details that if you started reading them in the evening, you would fall asleep. just inundated with all kinds of information. Opt report 2 gives a lot of information about it vectorized, it didn't, and what's the high level problem about it not being vectorized was, types of dependencies that exist. And lots of people just want to know if it got vectorized or not. And then they look at the loop and decide why it's that way and if they can change things to make it vectorized or not, as opposed to try and sort through all the analysis that the compiler spewed out to you at report level 4 or something like that. It used to be really simple, the way they would do the command line option. It used to be just minus opt vec report. It was just minus vec report, but then they made it a lot more complex. And in order to get a report, you say the level of the reporting now that you want, and then the phase that parentheses shouldn't be there, and what phase. And there's different phases that you can look at. So you can also specify, as you'll see in the lab, where you want that information to be stored, a file to store it in, and you can specify std out, so it will come to the screen. Because the default now is that it's going to go into a file, and then you have to compile it, open up the file, and then find out what it is, and then go edit your file. And that's a lot of work there. And so some people say, I really do want it to standard out like it used to be. And so you have to put yet another option here, which is a little bit long and crazy. It's, it's not Unixy. Unixy is, a minus AF or just some option like that with a few characters. This is more like C++. Okay, and you can do that with the GCC. Yes.
So when the loop not, so if a loop is not vectorizable,
yeah,
it could be a hardware constraint, or it could also be the coding or the application that
it's usually the coding and the dependencies in the coding. It's usually not, quote, a hardware constraint. That's usually, you write a loop, and if you have independent work in there and you've written it so that it is. Now, some algorithms, it's not independent work, and so it's not gonna be vectorized. And
shouldn't the registers be capable of intaking a vector as opposed to a scale, like we started at the beginning, the vectorized hardware?
Yeah, so there are limitations on the hardware in terms of how big these registers are. Are they 2 wide? Are they 4 wide in terms of double precision words? And of course, if you vectorize something that's only 2 wide, you're not going to get a whole lot of, well, quote, you get 2x of performance, but lots of times that does not happen. But if you have registers that are 8 wide and it can do 8 at a time, of course, you're going to get much better performance. And then that's a limitation there in terms of doing it. But it's, yes. Okay.
So the compiler can adapt to that register capability?
Oh, yeah, like the compilers. Oh, so you saw the different instruction sets that we talked about. You can specify an instruction set on the compiler line, and so you can compile it on one machine and say, hey, I know over here the units are only 4, compile it for 4 and put it over there. Okay. Yes.
You need to repeat the question.
Oh, so the question is are there hardware limitations in the in terms of vectorization? And the hardware limitations are generally how wide the vector units are, and it's usually the problem that there's a dependence in the loop on data accesses or data accesses, the stores or the writes, and so it cannot vectorize it and have it correctly provide answers. Yes.
So these compiler flags that you have up here aren't specific to OpenMP, correct?
No. And so, but what is specific to OpenMP is that OpenMP has SIMD directives that tell you that if that allow you to vectorize something that's not vectorized, and this is how you find out if it's vectorized or not. Otherwise, how would you find out if it's vectorizable? One way to do it is to turn off vectorization and then turn it on and see what the speed difference is between having vectorization on and off. You can turn vectorization off on the compilers, and that's a good way to find out in your code how well your code in general is doing in terms of vectorization. You know, you might have this big code and you go, I don't have no idea. I didn't look at all the loops. I don't know where the hotspots are. And so what you could do is just get a ballpark feeling of vectorization for your application. You compile it with vectorization off. There's a flag for doing that, and run it, and then compile it for it on, and then run it. And sometimes that's a indication of how much vectorization is being done, and the performance you get the gain you get from that. Okay. So here's an example of the output for a vectorization report, and it provides whether information, whether the loop vectorized, and whether the data was aligned or unaligned, and you get better performance usually when the data is aligned. And then what's really nice, I think this was a vectorization level 3, it tells you the cost of doing the operations if it's just a scalar, and the cost of it doing it for vector cost, and then the potential speed up that you would get because it's when it's fully vectorized. So that's pretty cool to have. And here's what happens when a loop is not. It just simply tells you it isn't. So these are good things to do. You typically find your hotspot in the code, and it might be just a single module or single file that contains those routines that are the hotspots, and then you turn on the report for when you're compiling that to see how well it's vectorized and what these reports are for those loops. Or you just do it for the whole thing, and then you look for the loops in there, and it gives you the line numbers. So as I said, the situation is that the data dependencies in the loops cause problems for, can cause a loop not to vectorize, and that could be because of the algorithm. It can be because of how the programmer specifically programmed it. And so the idea is that these things can be changed, and getting these vector reports is a good thing to see if you're doing well, and possibly learn why vectorization isn't being done and what you could do. So what is nice about things now is that before, if you had a function call in a loop, usually it wouldn't vectorize. And these days now you can have inlining. Sometimes that will allow it to be vectorized, but generally sometimes not. And what you can do is quote vectorize the function itself with the OpenMP directive called a declare SIMD. If you know that it's a vectorizable function. So it may not always be efficient. As a matter of fact, you'll see in your lab that there's a situation where you went to trouble vectorizing it, and it says, nah, this isn't going to work really well, or it's close to the speed of doing it serially, even though I vectorized it, and that could be because of accessing the data or many other things. So vectorization usually is a good thing, but sometimes not. And sometimes it's when you're striding, as I said, through memory, that's not good. High strides through memory is not good. Okay, so the things for achieving automatic vectorization is to stride, have a stride one through memory, avoid breaks and cycles, and continue statements within the loop, avoid pointer arithmetic, keep the loop simple, while loops aren't going to vectorize, and use a single data type in there. If you have a mixture of data types, it has to do a lot of conversion, and so sometimes that inhibits vectorization performance. And then you should use the optimized libraries when you can, like MKL, to do specific operations. So these data dependencies, you might have looked at this this morning. What inhibits a loop from being a work sharing loop or being parallel or being vectorized? It's these data dependencies. When you have something like this, where you're writing over to the left and reading on the right, and one iteration is dependent upon the results of the next iteration. So if I have B0 here, or B1 here, and B0 here, the next iteration, this is going to be, I'm going to, on this side, read from B1 and write into B2. And so that's going to read after I've written to it. Actually, you can swap this around, maybe have it the other way, but that's called a read after write dependency or a flow dependency. The other way down here is type of dependency is a write after a read. And so that's what's going to happen when I have A1, A plus 1 on this side. Note, it's just a matter of a sign here, whether it's a read after write or write after read type of dependencies. And in all scenarios, or both scenarios, that's going to have a dependence, and you cannot do, like I said, get all the data on one side and then do the operation and put it to the other because of these type of dependencies, so it won't vectorize. And the same applies for the read after, write after write. Here I have a write and another write here, and I'm doing something, a read, say, in the middle. I cannot exchange these loops or these statements in the loop, so it's not really independent type of operations, and therefore these things aren't going to vectorize. And then C pointers can hide these types of dependencies, and so the compilers have to be conservative in that respect, in that when they see C pointers, they could be pointing off to anything. They have to be careful about not vectorizing it when they should. So that's where the conservation or the conservative aspect comes in. And so one of the big things in helping the compiler is, of course, to remove these dependencies, and there's different ways. Sometimes reordering things it can eliminate this. One of the big things is that helps the compiler in vectorization and vectorization performance is possibly to fuse loops. Okay. So, and the way that works out is if you have a big loop and it's accessing things, large arrays, and it's coming in memory and coming in here, and then you're doing the same thing in another loop down here for A, it has to bring it from memory twice. And if you fuse those into a single loop, where you have a use case for A here and a use case for A in a loop below, and you fuse those, then you only have to access it once. So that works out. Sometimes fission and I guess splitting is a good thing, because you might have something in the loop that does a lot of, you might have a loop that does a lot of independent operations, but there's just one little part of, or one or two statements that's causing a dependence. If you split this out into a loop that now vectorizes for those independent parts and a loop that does just the serial parts, then you're going to get better performance because you have parallelized something that wasn't parallelized before. Still, you got to do this other serial stuff because of the dependencies. And so sometimes people have explicitly unrolled the loops themselves. Lars talked about that this morning, and gained performance from that because the compiler didn't know what to do. But I suspect in these cases now with some of these with SIMD directives, you can specify what you want to do. And of course, you can always change the algorithm and follow the guidance of the vector report. Okay, so the other thing is, of course, add SIMD directives, and these directives assure the independence of the operations. They say, I know what I'm doing, just do it. Do as I say. And these directives are generally for the loops. I guess they could be put in sections. I've never seen that. And of course, functions can be have declarations that they're quote vector functions. It's for C and C++ and Fortran, and it doesn't work with the, I guess, the C arrays at this point. But I'm a little bit. I know Silk does a way to compile it with the library. You can use C arrays, but I thought C arrays work, but I have no experience with that. So in OpenMP 4, that's where they first came out with these SIMD directives for the do and for loops, and then combining that with work sharing loops where you actually vectorize the loop at the same time and then split it across threads. That's when you have SIMD and work sharing, and we'll see that. And then declaring certain functions to be quote vector functions. And then there were a lot of refinements in 4.5. So one of the things, why do we need these? We need them for even simple cases like this. If you just look at this loop, it's pretty obvious that it is has independent work here in terms of what's happening over here and what's being shoved over here. But the vector report for this did not vectorize it. But if you put an OpenMP vector in there, or OpenMP SIMD directives in there, it will vectorize it and run correctly. Now we had an example for the lab for you doing that, but of course the compiler folks are always, you know, finding out what they need to vectorize and things that they've overlooked. And actually this case now does vectorize, whereas in the, compiler 17, I think in the 15, compiler, it wouldn't vectorize it and you had to put the pragma in there. But the pragma is very simple. It's just OMP SIMD, and it says, I know this is independent operations, go ahead and do it. So that's the nice thing about it, and it's portable, okay? The more complex thing about it is it has all these knobs and the clauses for you to specify to the compiler that certain things, that once certain things or that certain things are aligned. And so it has all these different clauses in here, and we'll, in the lab, you'll look at doing the collapse for a SIMD operation. You can have a collapse for the OpenMP work sharing. You learned that, do that this morning. You can also collapse loops as a SIMD operation. And what's nice is, and you couldn't do this before, but you can say, I want this vector operation to work here. And by the way, it's pretty complex because it has a reduction in there. And you could do reductions, parallelized reductions in with work sharing loops, and you could also do it with SIMD. Pretty cool. And then you can specify the alignment. You can specify the relationship between iterations, and then the lengths of you want that vector to be. You want it to use 4 of the 8 or just 2. There are reasons that you might want to limit that size, particularly if you have a code that's to work on several operating or several platforms that vary in size, but you have a minimum size there. So you have all these different operations to do. This, and here's the basic example here, do loop. This should actually vectorize, but here's the syntax for that. OpenMP SIMD. And so since the SIMD always applies to a loop, you do not have to have in Fortran the end SIMD down here. You can just say bang pound, bang dollar OpenMP SIMD, okay, for vectorizing it. Here's a case where you had a reduction in a loop and you want it to vectorize that, and it will do that. And you can specify that you have a reduction, just like in work sharing, and that you have a temporary variable. And so you're specifying that at a very close hardware level. And here's how you specify the safe length. And usually this is not the case where you'll see this. The usual case where you see this is that you have ace of I on this side, and then ace of I on the read side with an offset of, and you know that that offset's always going to be 8. So it says, hey, I can vectorize 8 elements of this at a time, and then and that's very reasonable to do that. And so I can get 0 through 7 over here on the right side, and all the data, and put it through 0, 7 on the other side with the offsets, and I'm okay. And then I do another set of those, and everything will be fine. Okay. So the other thing is that compilers try to inline, and sometimes they do not do a good job of inlining and then vectorizing the loops. What you can do is specify with OpenMP that you want that function to be inline as a vectorizable function. And that function just does something with some scalars or values, and then you say it can be done on an array of values for that. So here, foo, I'm asking, for each iteration, I send a value to the function, or have the function work on that and give a value over here. It appears just, you're really never sure, but it's taking these as values and giving a result. And it would seem like, and if you know that the operations in here are not affecting any other values in R, S, T, or A, then you know it could be vectorizable, and so you can declare that as a vectorizable function. And so you do that in OpenMP with the declare SIMD. You're going to declare this function to be a vectorizable function, and we'll see how you use that. And it has lots of the things that you would see with the specification just for the loop. And so the idea here is that if you have a loop that should be SIMDized or can be SIMDized, in the code itself, you specify that it's SIMD, and then wherever that function is that's being used in that loop, you annotate it, or what they say, decorate it with a declare SIMD, and give information to the compiler that if you know that the values are going to be incremented linearly, and they're aligned, or they're uniform or constant, that tells the compiler can use those for optimizing the functions, and whether it's in a branch or it's not in a branch. And so it would look something like this, that we had this foo up here. Actually, this is just the declaration and not the function. We'll see that in a little bit. But basically, you would, and even with the prototype down here, you would specify things about it, that it's SIMD, it's non-branched, and you could use 2 of them if you don't get it on a single line. Lots of people just put it on a single line. So you'd give information about the prototype or the function. This should be the same. And then you specify SIMD down here, and the compiler now knows when it goes to get foo, it looks up here in the prototype, says it has these characteristics. Good, that's a vectorizable function, and so I can vectorize this loop. in terms of how you annotate the functions. Here's an example of foo and bar used down here in two loops. And if I now specify that these are SIMD loops, I know that the operations on each iteration of these are going to be independent. Then whether I pass a single value here and increment it as array, or whether I do an address here, I can do it. I can specify that these are vectorizable functions no matter how you use these arguments here. And so, for instance, in the case of foo up here, I am going to send an array here, or not the array, but the pointer, and that pointer is going to be constant. So, and we're just going to increment off that pointer, and that's what that's doing. So for C codes that use pointer, you specify that that pointer is going to be uniform or constant, and then in here, we're using I and passing I to find a relative point to that, a relative value from that pointer to the array it points to, or the array elements it points to. And so we declare that I is going to be incremented, and it's just linear. And so when the compiler sees that, it says, I got all the information here. I know that R is always going to be constant. It's never going to change, where the call says, oh, I have P, Q, or R. It's always going to be R. And what's happening here is it's going to be incremented sequentially by stride 1, and so it can optimize this when it in lines, or when it puts it down here for making a vectorization. And so generally you would see this in some other file, and then in your driver, wherever you're compiling that, you're specifying it SIMD. You have the prototype, which also specifies this stuff up here. So in the main program or the driver, you have all that information that goes into this, into the vectorization here. And on the compiler side, when it's looking at the function, at the function, compiling that function, it knows that information. And so that's basically how it's to be used. And here's how it's done in Fortran. Note that it's in C, it's pragma before the function, and in Fortran, it's within the function right after specifying it, the function declaring the function name and attributes. Then you specify the OpenMP declare SIMD, and you can use in foo up here. I'm not sure. I think it's optional since it's in the function whether you put foo or not, and then specify how variables are used in there. And so down here, like we do in C, we simply say it's a SIMD function that's being used, or the loop is SIMD. Okay. Yes. Question.
So does it matter in C if those are placed in the header or the implementation files?
No, it should. Oh, the question is it doesn't matter if this is put in the header, in the headers? No, because the headers will be in line and the compilers will be included, and then the compiler will see that. So it can be put in the headers. Okay. The other scenario is that you can use SIMD instructions within a work sharing construct. So we now have this combined directive of parallel 4, and then SIMD with its clauses for the SIMD, or an additional clauses, whatever you need for the for statement too. So all the stuff, or you might say baggage, that you get with the for directive, or the do directive, you also get here. And and so here's an example of that. We have our simple loop down here, and here we just have the function. We've declared that that function is a SIMD function up here in our prototype, and down here we specify that, oh, this is OpenMP work sharing for, and that it's also going to be vectorized. Okay, so what happens here? You need to have chunk sizes in your for specification. If you're doing scheduling, you need to have chunk sizes as big as how wide you want your vectors to be. So if you have vectors of length 8, then your chunk size should be minimally 8 for these guys, not 1. Okay, so that's an important aspect of combining these. So there's some extra stuff that we'd like to go through that's not just about OpenMP, but might be important in terms of optimization in code, and that is being able to prefetch things to put it in the cache before it's actually needed, so you don't have to wait for it in a loop. And there are tools to see if this is needed, and which we won't discuss here. You can align things up, and the compiler now is pretty good about aligning things up, and there's not as many problems with misalignment and all these all this information in the reports that say it's unaligned, it's unaligned. It does sometimes now the compiler does a much better job of not having very much reduced performance because of unalignment. But on some of our other machines that was, and people would put alignment information in the SIMD instructions, as well, of course, to align the data, and we'll see how to do that. And of course, padding can always help. And basically, when you do align something, it just makes sure that the starting point is such that something has been padded where it has starts on it. So in terms of alignment, you can specify what you in C. Usually, instead of having a malloc, you can use the Intel _mm_malloc, that instead of just having a size of space to get, it also tells the alignment, align on 64 byte boundaries, and then you have to have the free. Now what's quite a few, what some people do is they use the POSIX alignment mallocer, and which is a little bit more complicated, but it's portable. This is not portable. This only works with the Intel compiler. And on the in Fortran, you can specify that something is, or you can specify an attribute for an array or a variable, and with this syntax, and specify the alignment in terms of 64 or 32 bytes this way. So in Fortran, you have a way to specify when the variable is created or the array is created, and in C for dynamic mallocs, you can either use the Intel or the POSIX standard for doing that. And here's an example of using their attribute for that. You can specify attribute align 32, and then specify declare your variables of a certain size. Or you can do a pointer and do your malloc this way. So this is on your stack, and this is on the heap, and then this is how you free it up on the stack. But that's, I mean, on the heap. But that's not portable. There's also another thing about C is the fact that people use a lot of pointers, and sometimes the compiler won't be able to detect whether there's an aliasing. That is, you have a pointer here and pointer here, and it looks like they're pointing to separate data. Well, they might be, quote, aliased, where they're actually pointing to the same data. You can specify, and when you have calls to functions, whether to use, to specify that it is restricted to no aliasing, and there's actually a compiler option called alias ANSI alias, which says there's usually, or for only specific cases, is there any aliasing that might go on here? And so that actually helps the compiler make sure that it can that it's valid to go ahead and to vectorize this. And so you have to have specify this restrict attribute in the arguments here. Instead of just calling float star a, you would also put in there restrict, and then when you compile it, you use -strict, and the compiler knows there's no aliasing there, and it's safe to vectorize for these within this function here. That it's if it's using these variables and they have different variable names, they're not going to be aliased. So C over here is always going to be pointing to different data than the A over here. They're not going to overlap at any point. So for C, that's an important concept to use. And then you can also do prefetching. Have a loop, for instance, in this loop, in this for loop here, you might want to prefetch values for A, and the syntax is here's the variable, and you can specify how far in terms of loop iterations you want to prefetch this variable. And here, there's not much of a reason to do this. The compiler should figure all this out. But in more complicated situations, there might be some variable down here that has to be picked up from memory, and it's always coming in late, and it has to wait a long time. And you could do a prefetch on that to get there before cache, before you even use it. So for instance, and this is even helpful at times when you have, like, you're calculating pi, you're not accessing memory at all, and before you sort of finish that up and you have a lot of arrays to access, you could do some prefetches to get things started rolling in from memory before you get out of that section of code or instruction set there that's just doing operations. So for performance, as I said before, the quick way to see what's happening in your code is to turn on no vectorization and look at the difference between vectors and having vectorization, and watching that time of execution. And so this is sort of a scenario for looking at different performances. And the big thing, of course, when in your codes is you want to do some profiling and find the hotspots, because you don't want to spend a lot of time vectorizing something that's not used much in your code. Okay, so that's it for SIMD quote vectorization. And what we'll do now, yeah, that's good timing. Lars, do we want to start the lab now, or do you? No. Okay. So, yeah. So we'll go through the lecture. Okay. So we'll go through the lecture, and Lars will come up and talk about affinity on these OpenMP. Let's see. If you have yours on the source, I can pull it down. Because if I pull this off, then you'll lose the connection to what the other viewers are looking at. Okay, then we'll do that. Okay. So.
You have the camera off?
Yeah, the camera's off and your mic is on, so you're live.
Okay, very good. Very nice. Okay, this is now about OpenMP affinity for pure OpenMP code, or more importantly, for hybrid code where you combine OpenMP and MPI. This segment is really not rocket science. What you want to do is you want to use all your resources. You want to use it in an even manner. You know, you have 20 cores, 20 threads. You want one thread core, something like that. So the objective is not rocket science, and how to do it is not rocket science. So I think we can go through it really quickly, and then you will learn more from the lab where you play around a little bit with the different settings than me talking about that for a very long time. The motivation is you have more and more cores on a node. The KNL systems that you have used for the labs have 68 cores, and they have, in quotes, hyperthreading with 4 threads per core, so you can have up to 272 threads or thingies that run on your node. The next generation of Xeon nodes that we will have in STEMP 2 will have at least 40 cores per nodes. They have hyperthreading with 2 threads per core, so you are already up to 80 threads or 80 things that you can run on a node. The operating system does something to spread out the load that you put on the system evenly, but it doesn't do a very good job of it. Often it works, but often enough you will have a situation where some cores are idle and some cores are oversubscribed, and so you basically have to deal with the affinity. And now you can do it through OpenMP. So if you use a node with a pure OpenMP code and you are using all the software cores, then the situation is relatively easy. But on the KNL, often you want to use only 1 thread or 2 threads per core, and not 4, or you just want to have 1 thread per core on a Xeon and not 2, or on a Xeon node you want to have 2 MPI tasks, 1 per socket, and then use as many threads as you have cores on a socket. And you don't want the threads of the MPI tasks that run on socket 0 flip over to socket 1 and vice versa, because that inflicts a lot of costs when you access memory. And so there are a bunch of reasons, all easy to understand, why you want to do the binding. And since now OpenMP has that in the standard, you can now vendor agnostic do that for your code, and you don't have to deal with the different systems. Main objective is use all the existing resources on a node. Everything is even. Oh, a difference between cores and threads. So when we talk cores, usually we mean cores in the hardware. Sometimes then we talk about hardware threads. Those are the threads that are provided by a core. In the old days, there was 1 hardware thread per core. Nowadays, you have 2 hardware threads per core on a Xeon, or 4 hardware threads per core on a KNL, generally called hyperthreading, although Intel applies that only to the Xeon and not to the KNL. A thread is the software thread is the thingy that you run in OpenMP when you start your parallel region, when these threads are spawned. So the threads in OpenMP have to match or will put on the hardware, on the cores or the hardware threads provided by the hardware. And what you don't want is have more threads in OpenMP than you have hardware threads, and sometimes you want to have less threads than you have hardware threads. Yeah, like we have in this line here, this sub-bullet, maximum is on KNL is 4 times the number of cores. On a Xeon, it's 2 times number of cores. You want to do an even distribution. So you want to place your MPI tasks, and you want to associate some cores to these MPI tasks, and you want the threads associated to the MPI task to be just on the number of cores, so that you can keep things pretty neat and distinct from each other. Pitfalls: you have too few threads, or the threads are not pinned, which means the operating system can bunch them up and leave other resources idle. Another problem is, it's not on that slide. We have 68 cores on the KNL. That is not a number that has that is divisible by a lot of other numbers. It's basically 2 times 2 times 17. So if you want to run 8 MPI tasks or 16 MPI tasks on a KNL, there will be cores that are kind of extra that you most likely don't want to use. And so that is why we do this. The easy part is you only have to understand two concepts, the concept of proc binding and the concept of an OpenMP place. Both are things that you set in environment variables before you start your a.out. The proc bind you can also change when you're inside your code, but for now it's perfectly fine if we just discuss how to set the binding policy and how to define places in environment variables before you start your a.out. Proc bind is super easy to understand. It's the bind policy. You can bunch threads close together, or you try to spread them out as far as you can. And places is also not difficult to understand. You have all the cores in your node, and now you establish OpenMP places on your node, and you assign cores or sockets or hardware threads to a place. Once you have these, you have places defined on your hardware. OpenMP will put or assign threads to these different places that you have defined. Within the place, a thread can move around, but it cannot leave the place it has been assigned to. It sounds more complicated than it is, but when you see an example, it will all become clear. So for a proc bind, there is close and there is spread. We put that in an environment variable, OMP proc bind, and spread is the master. And places, a place list or places are the smallest unit of execution. And from these places, you make a place list. So a place is, in curly brackets, 0. That is a hardware thread is 0. A place list could be a bunch of places, so 0, 1, 2, and 3. So this would be hardware thread 0, hardware thread 1, hardware thread 2, hardware thread 3. And now you have 4 places in your place list. If you now run with 4 threads, then these 4 threads would, the first one would be in this place, next one in that place, and and so on. There's unfortunately not an example of that, but a place can be also can contain more than one hardware thread. So it could be on a Xeon you have a dual socket a node. The first place could be the first socket, the next place could be the second socket, something like that. For convenience, there is some interval notation that we will go through as well. This part is for you to, we will play around with that in the lab, and then you will get the hang of it. What you later on really do is you use these abstract names, sockets, cores, or threads. Because if you use these abstract names, then your code most likely becomes very portable from one machine or one hardware architecture to the next. So if you say OMP places is sockets, and your hardware has 2 sockets, then you have defined 2 places, and your threads will be distributed evenly or in some form among those 2 places. If if your hardware has 68 cores and you say OMP places equal cores, then you have automatically or very easily defined 68 places, 1 for each core. Now you have 68 places, you have 68 threads. Now you immediately understand how you can evenly distribute your OpenMP threads among your resources. And yeah, that is basically it. And the rest becomes much clearer when we go through some examples. So here we have a hardware with 2 sockets. These are the green things here where the mouse is. Each socket has 4 cores. Now let's see, where do our OpenMP threads end up? We put OMP num threads to 4. We say OMP proc bind to close. We haven't talked about places in this example, but the default is to take the cores and make 1 place per core. So now you can see that the 4 OpenMP threads end up on the first 4 places or cores, because OMP proc bind is close. So it goes through the places and puts them there. If you do OpenMP proc bind equals spread, that's the right side of the diagram, then you see that the threads are spread out among the 8 places that you have available. And always think about round robin for everything that we do here. If we now we could achieve the same configuration by again putting setting OMP num threads to 4, but now we are defining our own places, and here in this example we define 4 places for the 4 threads. On the left hand side we do 0, 1, 2, 3. On the right hand side we do 0, 2, 4, 6, and we get the same outcome as we have gotten before. Just keep in mind, you define places, you have the number of threads, it puts 1 thread in a place, and when you run out of places, then you start at the beginning again. So if you had OMP num threads to 5, then the 5th thread would end up in the first place, which is core 0 again. So pretty easy to do. Here's an example how you could just a shortcut from places 0, 1, 2, 3 or 0, 2, 4, 6. We could use the interval notation, OMP places equal in curly brackets 0, repeated 4 times with a default interval of 1, or on the right hand side, place 0, repeated 4 times with an interval of 2. Now, all the new hardware has hyperthreading enabled, so let's look how that works, because the numbering of the hardware threads is cleverly selected, so you get a distribution exactly the way you want. In my example here, we have OMP num threads to 8. We have 8 cores. Each core has 2 hardware threads. These are the squiggly red thingies. Let's talk about the right-hand side first. We do OpenMP places is equal cores. So each core has 2 hardware threads. We have 8 places. We have 8 threads, so it puts thread 0 on core 0. Both hardware threads, it can move around there. It can move around within a place. It puts thread 1 on core 1, and so on. Now, on the left-hand side, we do OMP places equal threads. So now we have defined not 8 places, but 16. 8 cores, hyperthreading means 16 hardware threads, 16 places. Now, if we place 8 threads on that, we get a distribution where the first hardware thread on each core has 1 OpenMP thread assigned. So we get a nice distribution that way. Yeah, this kind of the same example, but with this interval notation. On the right-hand side, really nothing has happened. On the left-hand side, it's a nifty example on how to select the first hardware thread, that is the upper line, or the other hardware thread, that is the lower line. Because the hardware threads are numbered that you get the first hardware thread on each core first, that is 0, 1, 2, 3, and so on, up to 7, and then you restart with the first core, and now you get the other hardware threads. Mm-hmm.
So when we have quite an equal situation with the task that time to thread connecting and perform to either one or the other thread on that one.
Yes. So the question is, on the right-hand side, what does it mean when we bind one thread to a core, and the core has 2 hardware threads? So your place 0. Let's go to the previous slide, because then we don't have to. Oh yeah, OMP places is equal cores. So the first core is a place. The place has 2 hardware threads. We assign 1 OpenMP thread to a place, and within a place, the OpenMP thread can move around. So that's why the 0 here is expanded over the 2 hardware threads of a single core. On a single core, you don't really have to worry about which hardware thread is executing it. There's really no benefit from pinning it down any further. Yeah. So this one now illustrates on the right-hand side, OMP places equal cores, proc bind equals spread. You can see that the 4 threads are spread out. And on the left-hand side, you see that the numbering is selected in a smart way, so that close doesn't really mean the closest way you could imagine. We have 8 cores. We have 16 hardware threads, and we have 4 OpenMP threads. If you really want to pack them all together, you would have 2 threads on core 0 and 2 threads on core 1. But since the numbering is 0, 1, 2, 3, and then 8, 9, 10, 11 on the first socket, even with proc bind equal close, you are first filling up the different cores, and only when the cores, when you have gone through the first a set of hyperthreads, then you would put more threads on that core. So in the example on the left-hand side, you have 4 threads. They are close in the sense that they are on 4 neighboring cores on the same socket, but you are not filling up the hyperthreads before you have filled up all the cores. And that is really what you want. If you have, in this example, you have 16 hardware threads, and if you would use OMP num threads equal 8, you would still have, you want to have 1 OpenMP thread per core and not 2 OpenMP threads on the first 4 cores and then 4 cores idle. Does that make sense? It's really not rocket science. It is more just tedious. Yes. No, you could, in theory, you could have any number. But if you would assign 16 to this left example, then the first 8 would be on the first 8 hardware threads on each core. The next 8 would be on the other hardware thread. And if you had OpenMP num threads 24, then there would be a 3rd thread per core. It always goes round robin through the list. So once you hit number 15, once you have used hardware thread 15, which is the 16th hardware thread, if you still have OpenMP threads to distribute, you start again with the beginning of the list. Okay, so it is really it is tedious enough that I think you will get the hang of it when we do the lab, because in the lab you will play around with OMP num threads, with OMP places, with OMP procbind, and there's a little tool that will tell you where the threads are running. And then just by playing around with that, you will get the hang of it. Next point is discovering compute node architecture. When Kent did these slides, he put together a bit of overview for 3 commands that you can use to query the hardware that you have available: ls CPU, CPU info, and ls topo. Also, what you can do, and what we will do in the lab, is you can run a code, and in a different window on the same node, you can run top. And in the top window, the top usually shows you for one process, 1 line of output. But if you run a threaded code and in top you hit the 1 key, now suddenly you will get information for every thread that the OpenMP application is running. It will make sense when we go through it in the lab. Yeah, so this is lab stuff that we will go through in a minute. ls CPU, this is output you can derive: a number of threads per core, number of cores per socket, number of sockets with ls CPU, and a little bit of grabbing. You can do query CPU info, a cat proc CPU info that gives you a long file with a lot of information. And here, if you at the bottom, we have an org command that would create the list, the ordered list that you see here on the slide. So it's not the easiest way to do, but then you could get a list like this: physical ID, core ID, processor ID, and so on. And that relates to the pictures on the right. And yeah, let's try to finish before 3 so we have time for the lab. Hybrid computing is where you mix OpenMP affinity and MPI affinity. In hybrid code, let's say it differently. In pure MPI code, you have one MPI task per core running on your hardware. So if you're running on Stampede, it has 16 cores. Typically, you use 16 MPI tasks. If you do hybrid, you reduce the number of MPI tasks, and the holes that are left now in your usage of the cores, you fill that with OpenMP threads. So on Stampede with 2 sockets, a very typical application is you have 1 MPI task per socket, so 2 in total per node, and then you have 8 OpenMP threads per MPI task to utilize the 8 cores that you have available on a socket. This is for the KNLs, and we go through an example which has different number of MPI ranks. So if you have 1 MPI rank, then your thread number of threads could be 68, which is 1 thread per core, or 136, which is 2 threads per core, or 272, which is 4 threads per core. And for the other examples, it works out the same way. Because 68 is a weird number. If you use 8 MPI tasks or 16 MPI tasks, then you wouldn't use all the 68 cores, but only 64 cores in a setup that is evenly distributed. You shouldn't be too worried about that you leave some cores idle. Most codes are bandwidth limited, and 64 cores can already exhaust the whole memory bandwidth that you have, so you're really not losing much by leaving some cores idle. This is the example where you run 2 MPI tasks on a socket. So you start your Slurm job with -N2. Now rank 0 would have the cores 0 to 33, and rank 1 would have the cores 34 to 67. Here in red, you have the numbering for the hardware threads. And now we go through some simple examples. We have 2 MPI tasks, 34 cores per MPI process, and for illustration purposes, we now set the number of OpenMP threads to 17. We investigate what the different bindings do and what the different places do. So if we do proc bind to spread and places equal threads, then we will get the first hardware thread on every other core. Remember, 34 cores per MPI task, but we're only using 17 threads so that we have the gaps to for illustration. If we do the same thing with places equal cores, that is the second row, then the thread can move around among the 4 hardware threads on a core. If we do the last one, proc bind equal close, places equal cores, then we will populate the first 17 cores with a thread each, and then we would have 17 cores idle. And the third one is the one where I'm always a little bit unsure if that is correct. We do proc bind equal close, places equal threads. I'm not 100% sure if I fully understand why it is that, because I would have thought it would be on the first core 2 threads, it would be on the second core 2 threads, and so on and so on. But when we do the lab, you can try and figure out which one is right. And that already prepares the lab now, these slides. So you will do IDEF. In IDEF, you will run some dummy codes that spreads out the threads, and at the very end, it will create some kind of output where you can see where the different threads are running. This example is for MPI, but there's only an MPI example. Although in the lab we will do that differently. If you have 4 MPI tasks, your ranks are 0, 1, 2, and 3, and the output with the dashes here, it tells you which resources are allocated to that rank. So rank 0 can run on 0, 1, 2, and 3, which are the first hardware threads on the first 4 cores. The next MPI rank will be 4, 5, 6, 7, and then the next one is 8, 9, 10, and 11. So you have to, yeah, the digit here is only the last digit, and then for the other digits you have to go where the 10 is and the 20. And that is about it. There on the KNL there are 200 whatever 72 hardware threads, so the output can be really very, very wide. And if you look at the whole thing here in this example, what is it? It is 8 MPI threads, 8 MPI tasks. So you do S-batch-N8. So you have rank 0 to 7 here on the left-hand side, where I put the mouse. And each thread, each MPI task has the 4 hardware threads from core 0, from core 1, from core 2, and so on and so on. The other things are zooming into this upper diagram. And not surprisingly, since 272 is not divisible by 8, you will see that some MPI tasks have assigned 9 cores and other ones have only assigned 8 cores. And that would be something that you would have to manually correct so that all MPI tasks have only access to 8 cores. And yeah, we would have the lab, but we start with the SIMD lab first, don't we, Kent? Sure. Do we do SIMD first, or should I just do this one? And yeah, let's so this is fresh in your memory, and then we don't have to. Yeah.
So I have a very basic and elementary question.
No problem.
Out of all this configuration, how do you decide which one works?
So in the end, you test which one is the fastest. But the guideline is that you want to spread it evenly. You want MPI tasks to be on. You don't want to have cores, the hardware threads from one core, to be split between 2 MPI tasks. And you want to have at least 1 OpenMP thread per core, but you can experiment with 2 OpenMP threads per core, or on the KNL with 4 OpenMP threads per core. But the guiding principle is even it out as much as you can. And what is that? Recovered file? Where's my OpenMP lab? My Affinity lab, this one. Oh yeah. That's the right one. And the full screen. So this is the Affinity lab. We play around with different settings for OpenMP, for OMP places and OMP OMP proc bind. And the first 3 exercises are just for pure OpenMP, and then there's a hybrid mode on. We will use this little tool that Kent has written. It's called OMP Where Am I, or for hybrid, it's hybrid Where Am I, and that creates this output that I have shown you. You log on to the KNL. You have already done this. On the next slide, you will untar the OMP affinity masquerade.tar file, and then we do IDEF. And I'd ask you to do that, and then once you have made some progress, we can move on. Yeah, so this slide is probably the most important one. And also keep in mind that everything is on tinyurl.com tag-openmp-2017. So I will switch between those 2 slides back and forth. This is the one with the tar. No, I think what we should do is, let's get started with the first exercise, and then you can explain the exercise for the SIMD, and then participants can decide if they want to continue with the affinity lab or the SIMD lab, or in which order. Oh, this one, I would think in 20 minutes, yeah. No, I will go through, once everybody has untarred the file, I go through the IDEF, explain, and so once you're there, you do IDEF. And once you have your IDEF session running, I want you to open a second window and SSH into the same node where your IDEF session is. So in your IDEF session, you type host name, you get that name and use that to SSH into that same node from a different window. Do we have that? Oh yeah, that is basically the 3rd line here. So from the IDEF session, you know what the number signs, what that is, what specific node you are on, and then you SSH in, you are on already in your second window on the login node. You just type SSH and give it the node name of the node from your IDEF session, and now you have 2 windows on the same node. And we want to do that so that later on you can run this little toy code and do top. It is. I think I explained that in a more complicated fashion than it needs to be. You do IDEF, you get the name of that node. In the second window, you log on to STIM to log in KNL1 again. Then you SSH to that node. And in that second window, you do top. And then you hit the 1 key so you get information for all the hardware threads that are available on that node. And the second window, you make the font small and make it the window very long, so you have many lines, and you can move that thing around. Yeah, so let me rephrase the procedure. Maybe this way it is easier to understand. You have 2 windows on your machine. In both windows, you log on to login KNL1. In one of the windows, you type IDEF. Once the IDEF is through, you will know the node name where your IDEF session is running. It is either in the prompt or you just type host name. And then you use that name in the other window with SSH to log on to that same node. Okay. And so this is an example output that I did by hand of what we are going to do. You will see on the left-hand side here the thread number, and then on the right hand, to the right of it, you will see where this thread can run. So in my example, thread 1 can run on core 0 or hardware thread 0. Thread 1 can run on hardware thread 1. The next one can run on 3. The third one can run on 7 and on 22. And the last one can run on 6, 8, and 12. So this is highly irregular, so I did that by hand. And once we do the first exercise, you will see how this works. So do cdex1, and the README contains the command and the instruction. So what I want you to do is set the OMP num threads to 4, establish 8 places, do proc bind equal close, and then run OMP where am I, blank 1 blank pipeline cut -C1 to 60. And those in the README file, so with your mouse you can just cut and paste, and you will see some output. And I have that on the next slide. So run this experiment and then change the policy to, the policy to spread and run it again. Yeah, and on the next slide, you will see the result. We have defined the places to be 0, 4, 8, 12, and so on. And with proc bind equal close, your 4 threads will occupy the first 4 places, 0, 4, 8, and 12. And if you do it with binding equal spread, the threads will occupy the first place, the third place, and so on, which is 0, 8, 16, and 24. One question in the audience here. Let me clarify. We set OMP num threads to 4, and that is why our output has only 4 lines of output for thread ID 0, 1, 2, and 3. If you would set OMP num threads to 16, you will get 16 lines of output.
I think originally elaborated during the theory, but what happens if when you define your place list, you go over the number of
Yes. So the question is what happens, let's take this example. We have 8 places. If you put OMP num threads to larger than 8, you will restart at the beginning of the list again.
talking about the place list. Like that was to give a place that was like, I don't know, 1,000 gig.
Then you will get an error when you start your code that you have defined an invalid place. Oh, it's not a fatal error?
I don't think so. We just have.
Ah, hmm.
Where it didn't understand, and it goes, I don't understand this. So then it does what it thinks, but it actually displayed that, hey, I don't know what this is, if you put it there. And yes, it's a warning. It's not going to stop your code. There's a OMP display, OMP underscore display underscore EMD. They give you lots of information about your OpenMP environment. You want to set that variable and run an OpenMP, where am I or whatever, and you get some information about the environment it's running, and including
But
what it thinks the places is.
But let me summarize the response for the people in online. If in your OpenMP places variable here where the mouse is, if you put a number there that is invalid, a negative number, or a number that doesn't that is not available in the hardware. If the hardware has 16 hardware threads, then the largest number you can put there is 15. If you put something invalid there, you only get a warning at the beginning of the execution of your code, and places will revert to something like a default. Later on, you will effectively circumvent that from happening by using OpenMP places equal sockets, cores, or threads, and then it is automatically done regardless where you are. Okay, so we are with exercise 1. I think in the audience everybody was able to reproduce that. Now we redo exercise 1. So now we will pay attention to what output we have in the top window. In this case, you run OMP underscore where am I for 60 seconds, again with this cut command that creates the output that we had on the previous slide. But for 60 seconds, you should be able to see in your top window that the 4 threads are running on hardware thread 0, hardware thread 4, 8, and 12, and in the other case, 0, 8, 6, and 14. Because as always, you don't want to rely on some tool. There could be bugs in the tool. But later on, of course, you're running your own code that does not create this kind of output. So you're running your own code. You think you know what you're doing, but once in a while, it will be good to run your code and in a second window with top verify that you're running on the hardware threads that you have selected. In the top window, you will see on the left-hand side, it says CPU 0, CPU 1, CPU 2. So that is what top is using the word CPU to describe a hardware thread. So you will see the load on each hardware thread available on the hardware. And now you should see when you run this OMP where am I in the 2 different configurations, you should see a load on hardware thread 0, 4, 8, and 12, or in the other case 0, 8, 16, 24, and so on. Were you all able to do that? then we can move on to exercise 2. Again, a README text that contains all the lines that you can cut and paste. So in this case, we do 8 OpenMP threads, and each place is now 2 hardware threads, 0 and 68, 1 and 69, 2 and 70, and so on. So these are 0 and 68 are the first 2 hardware threads on core 0. 1 and 69 are the first 2 hardware threads on core 1, and so on. And again, you run OMP where am I 1, and then you change the number of threads to 16. So you run 2 experiments with number of threads is 8 and number of threads is 16. And on this slide, you can already peek at the results, but I'll give you some time to run the experiment yourself. So let me explain the result a little bit. So on this slide, I'm showing you the first 60 characters of the output. If you run it with 8 threads, we have 8 places and 8 threads. You can see that thread number 0, thread 0 is running on hardware thread 0, thread 1 on hardware thread 1, and so on. If you run 16 threads in 8 places, now you see that the first 2 threads run on the first place, and so and the next 2 run on the next place, and so on. Oh, I didn't. If you follow the instructions, you will see not only the first 60 characters, but the first 120 characters, and you will see that there is another diagonal coming up for the other half of the places that you have defined. So each place had 2 hardware threads, 0, 68, 169, and so on. In my output, I'm only showing the first one. Otherwise, it would get too small. And yeah, and this is exercise 3. So I think you know what you will have to do later on if you want to continue this lab. So now I think Kent will do the SIMD lab, and let's see that we can make some headway there. Should we change laptops?
Live, you can hear me. Okay, so what we're going to do is start on the SIMD lab, and it's somewhat self-explanatory in that you have directions. Go get the PDF file to go into a library, into a directory. In that directory, you compile code that is not vectorized, and you have the compiler options that you specify and run it, and it'll show you that, oh, it didn't vectorize that loop. And then you're asked to read the comments in the code, and the comments say, basically, you need to put a SIMD directive here, type it in, and then try and compile it. And if you've done it right, it should vectorize. And so it's just a matter of, yeah, I know how to vectorize it. We're not doing any timings. And so then there is another directory there that actually you can run some code to do some timing, and I'll have to show you about that. So let's first look at the general aspect of using the Intel vector reporting, and then how to use the SIMD vector loops. And you should look at the code, of course, when you're doing this. And what you do is log in, and you can do this on the front end. You don't have to do IDEV session and get to the back end. You're just using the compiler, finding out if things compile, vectorize or not. And so there are 4 directories there to do a couple things, and that is to vectorize something, telling it, I have an offset here, and I use a variable array on both sides of the statement as a read and write, and I have an offset, and if you put the safe length in there in the SIMD instruction, it will now vectorize it. The pointers, you'll see that if you have too many pointers in a loop, the compiler just gives up, but you can force it to keep going and vectorize the loop. How to do reductions in the reduction directory, and then collapsing loops. And look at the difference, or look what the report says about the loop collapse, if it's going to run faster or slower. We talked about doing loop collapses. Oh yeah, you get bigger space and it's going to work better. Well, read the vector report on that and see what it says. So what you do is SSH to the KNL machine. You untar the file that's in train called OpenMP, all lowercase, underscore simd.tar, and then you cd down in that directory. And you don't have to use IDEV. You can just do this on the front end. And the basic idea here is using the opt report options, all 3. You want to report at level 2, and then later on in one of the directories, I have you use an opt3 that gives more information, and there are instructions in each one of these directories what to do in terms of how you compile it, which is basically the same in all of them. And you either do it for the C code or the Fortran code. So, you know, if you're, yeah, I feel sorry for lots of the Fortran people because sometimes we don't provide them code. And as a matter of fact, the guy who first wrote these, there were just C codes there. And so yesterday I wrote a bunch of the Fortran stuff. So you Fortran people can have fun too. Okay. And so there are 4 directories there that you go into. Read the report and the code comments, and they tell you what to put in there, and then just recompile. Important thing, very, very important. You put your SIMD instructions in there, and I have you compile it. And you see these instructions here with just the compiler line. When you put the SIMD instructions, what do you have to do? You put OpenMP SIMD instructions. And now what do you have to do? What's wrong with this compiler line here? Yes, you have to put the minus, and it will silently say, and not say, it will silently just go and compile it and say, I didn't vectorize it, you know, when you do it. So a common mistake is you put these SIMD instructions in there, you don't put the OpenMP, and it just doesn't. And of course, if you've been in an OpenMP session like this morning, it's drilled into your head. But if you're out there just coding stuff and you say, I want that to vectorize, you're not thinking OpenMP loops. Work constructs, work sharing. You're just thinking vectorization. You put it in there and it doesn't work. It doesn't work. And you go, oh, forgot to put the -q OpenMP option on there. Okay. So there's another folder there called VEC. And unfortunately, we had you do some operations in there in terms of doing an alignment on a function. And we had you just read the code, and we had you do, there was an aligned function and an unaligned. And on the aligned function, you were supposed to put the directives in there to make sure that the arrays were aligned with the mmmalloc. And lo and behold, you don't get any speed up, because if you read the reports, they're vectorized in both cases. And I mean, not vectorized, but that's a different case. If you look at the times for this, they're exactly the same. And even though you put the do the mmmalloc, and that's because the compiler does a good job of actually aligning these things to begin with. So that's a canceled one, but you go ahead and look at it. And in the folder, what we have done is taken that and put, as you would normally have, a function in another file and your main program over here, and you compile them separately, like I show here, and then execute them. And so what happens in this case, the compiler's not going to inline that function over in main, and it doesn't even know it's vectorizable. And so in this case, in the vector folder, you have to put the declare SIMD type annotation in the function in file declare _B, and then in the declare _A, where you have the loop, you have to declare it a SIMD loop, and there's comments in these codes to tell you what to do. And so after you compile it, after you make the changes and then compile it with the -OpenMP option, it should run faster, and you'll see it runs about twice as fast. And so this one's good to look at for making functions, quote, vector functions. And then the other ones are just really good, are good examples of doing, making a SIMD directives vectorize things. So once you spend about 15, 20 minutes doing that, and then we have one short session after that, which would be a hybrid computing. And how many people know what hybrid computing is? Oh, there's somebody in the back. It's when you combine OpenMP and MPI. And you'll see it's rather simple to do. Quote, rather simple. It's actually programming and making sure you get everything right. That's a little bit difficult in there, but it sounds daunting, but it's actually really simple to do.
So what if you run OMP SIMD?
Yeah.
Do you have to include that into like a more general Pragma OMP parallel, or does that?
No, you can, that's a quote, that's a stand, well, it's not quote, that's all you need. You know, it doesn't need to be with a parallel or a parallel do, it's just Pragma, OMP, SIMD, and whatever. No. Oh, in Fortran, no, you don't. You can put one in Fortran, but since it applies to a loop, that's it ends where the loop ends. Yeah, it's like the OpenMP parallel 4 or the OpenMP 4, I'm sorry, OpenMP do or OpenMP parallel do. You don't need that final end statement because it's a do loop. It knows where to end. So you don't need it. You don't need it with the SIMD either. Okay. Has everybody untarred the file getting down there? Okay, good. Afternoon. It's 4 o'clock. We're getting close to the end. And what I'll do is keep this last session short for hybrid computing. I had some stuff about affinity at the end, but Lars went over that. And so you're well aware of the importance of affinity, and it even becomes more important hybrid computing. One of the things is what is hybrid computing? And that's the marriage of MPI and OpenMP in a single code. So, and how does that even get launched? We're used to just typing the A.out for OpenMP, and it spawns the threads. And then from this single A.out, boom, you have a bunch of threads, and you look at top, and that's doing some sort of computation for you, and that's fine. And then we got the other side of this, where we have MPI with multiple tasks. And actually, when you have MPI with multiple tasks or multiple ranks, each one of those is an A.out spawned by the MPI run. So the problem maybe with this session is you need a little bit of MPI experience. And so let me ask you, how many of you have done MPI, have not done any MPI computing? Just one person. Two. Oh, two, you went to a class 2 weeks ago, so you still have an idea. Yeah, you have an idea about it. And so what's MPI for? It's for sending messages between nodes on the computer across the network. And basically, you can think of OpenMP as doing work on the node and not being able to get across the network. Okay, and so we're going to marry both those, and we're going to have a task or an MPI process on a node, and it's now has communication capabilities with all the other nodes. And in there, we're going to have a parallel MPI, OpenMP stuff. We're going to have parallel directives in there to say, hey, just do this parallel, put some threads, execute some threads in the background, and here is my MPI process. Okay, an MPI process is just like an A.out, which, you know, you compile something, you get an executable, you know, and it's, you just have it start executing on multiple nodes, or you can have MPI running a couple tasks on a node, and we'll see that in a little bit. So the code that you write for MPI that runs on each of these nodes and can connect with each other and pass messages or data back and forth is going to be, think of it as the container for the OpenMP executions. You have this process called the MPI process on that node. It has connections to the outside world, and in there you're going to put some OpenMP code, okay? And we'll see some simple examples of this, and it will hopefully make things clear. And so the MPI processes are communication between nodes. That's the important thing about it. And the nice thing about OpenMP is the fact that it's a shared memory paradigm on the node, and these threads can see each other's memory. And so things might, and so OpenMP code has sort of privileges that MPI has. MPI tasks, MPI ranks executing someplace can only talk to another one through communication, and its memory is access is confined to that process. Okay. So here's the world view of this, that our hardware view is that on one side of this diagram, on a node, we can have, say, 16 MPI processes launched on a single node. I mean, we can launch them on separate nodes, or we can ask for 16, 1 or 2, whatever, on a single node up to the number of cores. Okay, And when they do their communication with each other on a node, if say I had 16 cores here and I spawned 16 MPI processes, those MPI processes are real processes in the sense that they have their part of the memory that they know about, and they can't see anybody else's memory at all. Okay, it's like if you opened up PowerPoint on your machine, and in some other application, they're not allowed to look at each other's memory. They're different processes, and so every single MPI rank or task is a different process. So we can have that run, fill up all the cores on the node. On the other side of this, on a node, we can have forked 16 threads to fill up and execute that. Which one's faster? Which one's which one's going to do you better? It depends upon the scale of the calculation. So if I'm trying to do communications and I'm doing 16, or let's say these KNL nodes, how many cores on the KNL node? 64, 68, 72, something like that. Okay, what if I want to compute across 1,000 of these? And I'm going to put 64, 68 MPI task on a single node and have them communicate to all the other. That's going to be a big bottleneck for the interconnect. Okay, and so the way to do that is just to have one or two tasks, or four maybe, MPI tasks per node orchestrating things, and underneath are in them, each one of those running OpenMP, okay? And that alleviates all the communication connections that would exist if we just had a pure MPI code running like that. Yes?
But do these sub-MPI tasks necessarily have to communicate with the one outside?
They don't necessarily. The question is, do they have to communicate with the outside? No, but generally when you write code in MPI, you might do a finite difference where you have neighbors talking to each neighbors in a stencil. And there might be, if it's done right, there's just local communication, and that's faster because it doesn't have to go out on the network, and maybe it's just the edges of these that have to do that. But still, when you're working with 16 or maybe even 24, maybe that's not bad. When you start saying, hey, to get my performance, I want to run 68 MPI tasks on this KNL, and now I want to do it across thousands of nodes, then you might have a problem. So that's why it's reasonable to have just a few of these MPI tasks doing the communication on a node, maybe up to 16. That's fine, and it's not too bad. And then have the OpenMP do some work in there. And so what you'll see is this scenario where, for instance, a good situation where you have one MPI process in a node, and that MPI process is going to have a parallel region in it and fork the threads for doing some work there. And you let this one MPI task do the communication between the nodes, okay? And so you would envision, you could, well, or you can envision maybe having two. And the reason why there are two here is because we have two sockets, and you'd maybe want one on each of the sockets. Or in the KNL, we only have one processor, one socket, right? But there are these things called NUMA nodes in there that have sections of it close to certain parts of the memory, like in here. And that's a whole different story about NUMA, non-uniform memory access, in that if you look here, here's a socket, here's some memory on it. Probably this is a better picture. Here's a socket, and here's its memory connected directly to it, and another socket with memory here, and they have an interconnect quote through the processors to each other. And if I'm a process here and my memory's over here, I have to go through this interconnect here to get the memory, as opposed to maybe picking it up locally here. This is called non-uniform memory access. It's all one big shared memory, but depending upon where your process is, there may be a little bit of delay if it has to go across here. So it makes sense on some architectures where you have two different sockets to have an MPI here with all of its threads accessing this, and it has its separate memory space because the thing that spawned this was an MPI process, and it only had a certain amount of its memory available to it on the system. And the same way with this guy, processes cannot see each other's memory. And so this process that starts here starts this MPI parallel region with these threads, and these threads can only see the memory that's associated with the MPI process. And so that's why you might have two per node. Lots of times you'll just see one, and people are trying all different kinds of things here. And so again, this sort of container idea of hybrid computing is the fact that we will start with the MPI init. That's how you start an MPI process in a code, and at some point then you end it with the MPI finalize. So you saw that last week, and in the code you have that, and that means after it hits the init, it can communicate with other MPI ranks that might be on the same node or another node. Okay, and that's fair enough. And the idea is that inside this container from the init to the finalize, you'll have other MPI calls, but we can put a parallel region in there that would, oh yeah, so we could put a parallel region in there. Now you might think, well, can I do something else? Yeah, you can have, after the finalize, you could have a parallel region, or even before the MPI init, you could have a parallel region to do OpenMP. But the general rule is that you lose your communication ability, or do not have communication ability to other ranks or MPI processes outside that. And so generally you don't see that because you don't have communication capabilities to any other nodes after this. So usually you start a program or a package with the init and finalize, and you do everything in there, and it makes sense that that's where you would have your MPI or OpenMP calls. And so this is all it looks like. It's this simple, where you have your init, some MPI communications in there, and someplace in there you just simply have your OpenMP, OMP directive to fork some threads, and those threads are going to do some work sharing or something like that in parallel on there. Okay, and so what that means is, if you go back here, that if I have 16 cores on a node, and I have one MPI process, I want to be able to spawn, I set my OpenMP number of threads to 16. If per 16. And so each process that starts and has a parallel region will have 16, and there's only one. If I'm going to have two MPI processes on that node, then there's 16. I want to split those up, and I want to then only have 8 threads per process. So I would set OMP num threads to 8 in that scenario. And so you would do things like that. How many MPI tasks am I going to do? Well, I'll do so many, and then what I want to do is have enough threads to occupy all the cores and keep them busy, because that's the important thing about HPC, is you want work to be done on each of the cores and do parallel things. Okay, and okay, and yes, I went back. Okay, so that's all we're going to do is put a parallel region in there. And what if we did want to do an MPI call in a parallel region? There is a problem with doing that. In the fact that you know about things that are shared in there. And if you have multiple threads accessing a shared, you might have a race condition exist if they're trying to update things. And so code such as MPI for the longest time wasn't thread safe. You couldn't do this. You couldn't make an MPI call here because there were global variables it had to touch. And if you had two threads doing, say, MPI send receives, there may be a variable someplace there that they're both touching and having a race condition. So you might get it all, the whole thing all locked up. So MPI initially, when it came out, was not thread safe. And the point is eventually they made it thread safe so that you could have MPI, like one or two or MPI calls within this area here. But the big difference is that your initialization would be different. In the previous case, you see it's just MPI init up there, and now you have to do an MPI underscore thread, MPI init underscore thread. And basically that's just saying that when you load up the libraries, you have to get the thread safe libraries. So it understands that. It says the SO shared object file will be now the shared libraries. I mean the thread safe libraries. And would they run slower? Yeah. So good reason not to put any MPI calls in here and worry about all that. And in general, you see the situation where people are not using the thread safe version because it may be slower, and it just gets more complicated to do that. You know, which thread's going to handle this in a parallel region? I have to put if statements around it. So it makes sense to do it the clean, old-fashioned way of just region and of just a parallel region. And this is exactly what it looks like. Number one is that you have to have both header files for OpenMP and MPI at the top. You have your init and finalize. You can do you can do calls here to MPI, and basically this in the OpenMP world, they call it the master thread. Okay, but really it's the MPI process. Okay, whether you call it the master thread of OpenMP or MPI, it's the process. And in here, I can have my parallel region, and that just forks some threads that get splat onto the different cores according to affinity. Okay, so the important thing with hybrid is you have to worry about the affinity for the MPI process, right? That's the first thing that gets started. Over here, when I'm trying to do this, I have to have the affinity set so that MPI knows to put one here and one here. And that's what's, yeah, there's some things you do to do that. Then the other part about that is that once you set the affinity for this guy, which says, oh, I can execute on any of these cores here, the MPI, I mean the OpenMP of when threads are forked inherits the mask of the parent. So the parents, the MPI process, forked threads on there get their mask from the, or where they can run from that MPI process. And then the OpenMP runtime says, did you set an affinity for my threads here? If you did, fine, I'll adhere to that. And so in general, if you don't set any OpenMP thread affinity, once these threads are forked here, they can run any place at will on all those cores. And if you do something very precise like places with OpenMP threads, then or OpenMP, then you can prescribe where to bind them. Okay, there's a difference between having a mask that lets all these float any place. Basically, that mask could be, if this is process ID 0 through 7 here, all the bits would be set, and any process, and that would be the same for any process, and that says you can run any place on those. And when you do set the OpenMP affinity, you usually want to bind a thread to a particular core or to a process ID. And that's a lot of discussion there. We could talk about that for an hour, but I just want you to know what's happening there. And so, oh, we're supposed to quit at 4. Oh, I'm sorry, guys. I thought we were going to 5. Please excuse me. Okay. And that's basically it. In that, how do you get these things to run? You have to provide how much details for running on the MPI up there, number of nodes, number of tasks, and then do our OpenMP threads, set the number of threads. And each task will get that information. And so we have one thread, one node, one task, 16 threads. And like I said before, if we have 2 tasks, then we're going to set OpenMP threads to 8. And that is pretty much what I wanted to show you. And so we're not going to discuss the affinity, which all these other guys are going to do. And we're going to call it quits here. And you know about getting affinity information. Lars went over this. You can use this LSCPU. Oops. And, oh, I'm sorry. I'm looking at the wrong one. Okay. Or you can use, you get the, what I call the process IDs from this proc CPU information that says where your physical ID is. This is a socket 0, socket 1, and there's some numbers. And that's it. So let's call it a wrap. Thanks for staying later. I appreciate that. All right. Good.